Okay, the last lecture in this series I gave around 10th March 2020, and of course after that the lockdown started, so we are resuming after a break of 16 months, and let us restart from the point where we left off. In the previous lecture I considered inclusion of matter effects in three flavor oscillations, but the discussion in that lecture was partial because I will explain I'll briefly recollect what I did in that lecture. We wrote the time evolution equation for the three flavors. No, I think this is U. U 0 0 0 0 delta 2 1 0 0 0 delta 3 1 U dagger. So this is of course the Hamiltonian in the mass basis, and to go to the flavor basis we multiplied by the PMNS matrix, made the similarity transformation, and then we added the matter term which is diagonal in the flavor basis. Mu E, mu tau. Now if you multiply this out, you get some complicated symmetric 3x3 matrix. You add it, you get another complicated 3x3 symmetric matrix, and to diagonalize it and get the eigenvalues, eigenvectors, you have to solve a cubic, and the solution of the cubic of course is much more complicated than solution of a quadratic. So the algebraic solution here is quite complicated, and in order to get an algebraic solution we made an approximation. Since delta 2 1 is much less than delta 3 1 in magnitude, we approximated, so sort of tried setting delta 2 1 equal to 0, and this is of course an approximation, but this is as I discussed in the previous lecture. In this approximation we can solve this problem exactly, and we got the matter modified mu to mu E oscillation probability, which is sine square theta 2 3 sine square 2 theta 1 3 matter sine square 1.27 delta 3 1. So by the way, we set delta 2 1 equal to 0, which means nu 1 and nu 2 are degenerate, so the theta 1 2 rotation doesn't matter, and that is why we don't see theta 1 2 anywhere in this expression. And we have delta 3 1 matter is equal to delta 3 1 cos 2 theta 1 3 minus a whole square plus delta 3 1 sin 2 theta 1 3 whole square, the whole thing under a square root, and sin 2 theta 1 3 matter is equal to sin 2 theta 1 3 times delta 3 1 and also in the last class I discussed that if this is the exact formula, and that is if delta 2 1 actually is equal to 0, then we can utilize this formula to calculate, to find out whether delta 3 1 is positive or negative. We find that when delta 3 1 is positive, sin 2 theta 1 3 matter is larger than the vacuum value, whereas when delta 3 1 is negative, sin theta 1 3 matter is smaller than the vacuum value, and based on which we can tell whether delta 3 1 is positive or negative. But that is true only if delta 2 1 equal to 0, and if you consider that the case when delta 2 1 is not equal to 0, you find that life is more complicated. And first, it is complicated theoretically, but if we somehow struggle and solve the theoretical problem, it is also complicated from an experimental point of view. So let us see how that happens. So the evolution equation is there, but let me rewrite that in the following manner. So what I have done is the Hamiltonian in the case of delta 2 1 equal to 0, I have put here in the curly brackets, and the part of the Hamiltonian that depends on delta 2 1 I have written separately, and you can guess why I have done so. I treat this as my H naught, and I treat this as my H perturbation. And I have already solved the eigenvalue problem. I have determined the eigenvalues and eigenvectors of H naught, and using those eigenvalues and eigenvectors, I use this H perturbation to calculate the change in eigenvalues, change in eigenvectors. So I have, when I finish that calculation, I have the perturbed eigenvalues, perturbed eigenvectors, and I can use these perturbed eigenvalues and perturbed eigenvectors in my oscillation formula and derive the nu mu to nu e oscillation formula for the case when delta to 1 is not equal to 0. I can describe the calculation in few words. In 1 minute, I can describe the calculation. But if you start doing the calculation, there are fair amount of details to worry about. It's a straightforward algebra, but you have to do the algebra carefully, and it takes time. And the first calculation was done in 1998 or so by two different groups. And if you do the calculation, you get the matter modified nu mu to nu e oscillation. The leading term is same as what I have written before. The sine square theta 2 3 sine square theta 1 3 matter, rather sine square 2 theta 1 3 matter. Sine square 1.27 delta 3 1 plus order alpha correction plus order alpha square correction, where alpha is remember, when you do perturbation theory, usually there is a small parameter sitting in front of the perturbing Hamiltonian, and we do the perturbation expansion in terms of that small parameter. So here that small parameter for us is the ratio delta 2 1 by delta 3 1. And we calculate the first order correction, and we calculate also the second order correction. Here little bit of chronology is important. I told you, why did we need to go to the second order? Why not stop at the first order? To explain that, we have to consider the chronology. By 98, we knew that delta 2 1 is non-zero, delta 3 1 was non-zero, and delta 2 1 is at least some 30 by a factor of 30 or 50 smaller than delta 2 1. That one was known. But there was only an upper limit on theta 1 3. We didn't know in 98 whether theta 1 3 is 0 or not. It was hoped that it is non-zero and it's moderately large. But our guide in all these issues is experiment, and experiment says there is only an upper limit, and in principle theta 1 3 can be 0. So in a calculation, if you are doing a calculation, you can't neglect second order of a non-zero quantity with respect to a zero quantity. So just to be safe, people did this calculation up to second order. But in 2012, theta 1 3 was measured, and we know that sine 2 theta 1 3, which enters this calculation, sine 2 theta 1 3 is 0.3. Sine square 2 theta 1 3 is 0.09. Whereas this delta is roughly 1 over 30, that is 0.03. So now, since 2012, we know that this is a factor 10 larger than this, and this is a factor 10 larger than this. So in our present day discussions, we can afford to neglect this, but In 98, when the calculation was done originally, we had no idea. So just to be on the safe side, people did the calculation up to second order. And if you do that, the answer comes out to be first. Here I have introduced various bits of notation. Alpha, of course, is delta 21 by delta 31. This delta hat is 1.27 delta 31 L over E. So that's a dimensionless number. And A hat is A divided by delta 31, which is also a dimensionless number. I have introduced three dimensionless numbers: alpha, delta hat, and A hat. One thing which you should immediately notice is sorry, I've written the expression here itself, so I don't need to go up. So the leading term here and here, they are looking quite different, but one can show it with a little bit of algebra, that sine square 2 theta 1 3 matter is approximately sine square 2 theta 1 3 divided by 1 minus A hat whole square, or sine 2 theta 1 3 matter is sine 2 theta 1 3 divided by 1 minus A hat, and this delta 31 hat L, this 1.27 delta 31 hat L over E is approximately 1 minus A hat times delta 3. delta hat. This comes in the sort of, if you judiciously neglect sine square theta 1 3 relative to cos square theta 1 3, these formulae come out quite easy. And of course, you see why we have taken this 1 minus a hat from here and put it here, because in the limit a hat tends to 1, this quantity is finite. Whereas if this 1 minus a hat is part here and 1 minus a hat remains here, then it looks a little awkward. There is no divergence anywhere, everything is finite. So the reason I have written this formula in this format is, well, two reasons. This is the format in which it was originally derived, and this is the format this is what you see in almost any paper that you refer to when you consider matter effects in three flavor oscillations. But most importantly, for our discussion, this formula, which is an approximate formula to some extent, because it's a perturbation expansion in delta to 1, and also in writing these expressions we have neglected sine square theta 1 3 relative to cos square theta 1 3, but there is a lot of physics to be extracted from this expression, and that is going to be the next point of discussion for us. So first, let me list what are called the three unknowns of three flavor oscillations. One thing I have already discussed, that is sine of delta 3 1. And second thing, of course, is value of delta Cp. As of now, we don't really have an idea of what the value of delta Cp is. And the third one is what is called octant of theta 2 3. If you remember from our discussion about the effective two flavor approximations, then the accelerator neutrino experiments which determine theta 2 3, what they determine is actually sine square 2 theta 2 3, and they find sine square 2 theta 2 3 close to 1. But which means sine 2 theta 2 3 is close to 1, we take the positive value. But that would mean theta 2 3 is close to 45, but theta 2 3 can be lower than 45 or higher than 45. In particular, if you vary sine square theta 2 3 between 0.35 to 0.65, that is roughly 1/3 of its possible range, you find that sine square 2 theta 2 3 varies from around 0.92 to 1, less than 10% of its range. So, and we would like to know the value of theta 2 3, not sine 2 theta 2 3. So that is called the octant problem, octant of theta 2 3 problem. You have a question?
So theta 2 3 is close to 45 degree.
Yeah.
But we don't know if it is 45 plus or minus.
Yeah.
But why is it so important? Why are we drawing a line at quadrant?
Well, it is important at the moment from an experimental point of view, well, from an experimental point of view also it is important, because you see there is a sine square theta 2 3 sitting there. So is it 0.35 or 0.65? That makes it a factor of 2 difference. That is, so it is important from the point of view of experiment. And from the point of view of theory also, it is important because there are some discrete symmetries which predict it to be larger, some discrete symmetries which predict it to be smaller. Or if the symmetry predicts it to be exactly theta 2 3, then presumably there are some radiative corrections which will make it move away from theta 2 3. Now, should those corrections be positive or negative? So, knowing the information on theta 2 3 helps us in distinguishing between models. That is the theoretical interest. And of course, the experimentally it is interesting because of that reason. But you see the problem. There is the first term contains sine square theta 2 3, and also it depends on sine of delta. Second term depends on sine of delta. It is not sensitive to theta 2 3 so much because it is sine to theta 2 3, but it is sensitive to delta Cp. So this measurement we have, P nu mu to nu e, it depends on all three unknowns. So trying to measure, very simple, when we learn to solve equations, in order to determine one unknown, we need one piece of information. If there are two unknowns, we need two pieces of information. And if there are three unknowns, we need minimum three pieces of information, three independent pieces of information. But if you say I have one experiment in which I measure nu mu to nu e, I have one information and three unknowns, and I have a problem. And in fact, this was a point soon after the derivation of that formula. This was a point of discussion in a lot of papers. There was what is called a eightfold degeneracy. Why eightfold degeneracy? Mind you, theta 1 3 was not known at that time. So even if you assume theta 1 3 is non-zero, if I have one measurement of nu mu to nu e, if I measure nu mu to nu e, then I know theta 1 3 is non-zero. Good. But problem is, I don't know what theta 1 3 is. I don't know what exact value of theta 1 3 is. And I don't know about octant of theta 2 3. I don't know delta Cp. I don't know sine of delta 3 1. So I can have correct value of theta 1 3 and exact values of these three. But there is a uncertainty of 2 here. Okay, this is a continuous variable, but let us discretize it by saying delta Cp in the upper half plane, delta Cp in the lower half plane, 0 to pi versus pi to 2 pi, because upper half plane versus lower half plane, this term will change sign. So even though this is a continuous variable, I have discretized it. And here also, this is a continuous variable, but I can discretize it by asking sine square theta to 3 less than half, sine square theta to 3 greater than half. So if I consider these discretized values of these unknowns, then you can imagine 2 times 2 times 2 possible 8 combinations. And so once I measure nu mu to nu e, if I choose combination 1, that fits to some value of theta 1 3. If I choose combination 2, that will fit to some other value of theta 1 3. So I will have 8 possible solutions. So that's why people used to talk about an 8-fold degeneracy. This was a very hot topic of research for about 5-6 years. And of course, people were proposing lot of experiments that could be done to resolve this 8-fold degeneracy. But luckily for us, we don't have to face this 8-fold degeneracy, but we do face a smaller degeneracy. Let us see what that is. But one can show that if I have a precise measurement of theta 1 3, then these 8 degenerate solutions will actually split up into 1 plus 3 plus 3 plus 1. How does that happen? We will discuss in a minute. But you understand why this precision of theta 1 3 matters. I mentioned before that each of these has 2 possible values, so total 8. And given one measurement of nu mu to nu e, I will have some value of theta 1 3 with which I can match whatever combination I choose with the corresponding theta 1 3 value. I can match the experiment. But in an independent experiment, I measure theta 1 3 very precisely. So for 8 combinations of these unknowns, I have 8 different values of theta 1 3. But if I know the value of theta 1 3 precisely, then I can rule out the wrong values of theta 1 3. But so that provides a solution to our problem, but it does not provide a full solution. Why that is, I will explain now. So first, let us calculate the vacuum value for P nu mu to nu e with delta Cp equal to 0 and delta T is equal to 45 degrees. This is purely a theoretical calculation, and I call it my P mu e reference. Now you see that P matter with delta 31 positive delta Cp equal to 0, delta theta to 345. This is greater than this P mu e reference, whereas if this is negative, then it is less. And similarly, you find that P vacuum with the delta Cp in lower half plane, theta to 345. This is greater than P mu e reference, and if this is in the upper half plane. And this I have explained. This one has to work out a little bit of algebra to see. And you also see that P vacuum with delta Cp equal to 0, theta to 3 greater than 45 degrees is greater than P mu e reference, whereas if this is less than 45 degrees, this is less than P mu e reference. So this discretized values of the unknowns, one discrete value makes the P mu e larger, other discrete value makes it smaller. Now imagine if all three increase P mu e. Suppose delta 31 is greater than 0, delta Cp is in lower half plane, and theta 23 is 45. So each of the unknowns takes the value which boosts up P mu e. Then I will have a very large value of P mu e, and that's a unique solution. So theta 13 I know precisely, so there is no confusion there. And if I measure a very large value of P mu e in experiment, and the only possible way I can get that large value is I need a boost due to sine of delta 31, I need a boost due to delta Cp, and I need a boost due to theta 23. Only all three boosts it will the theory match my experiment. Then I have a unique solution. Similarly, I measure a very low value of P mu e, which means I need a suppression due to all three. Then I have a unique solution. So that is how I get that 1, 1. But imagine if two of them boost and the third one reduces. Then compared to my theoretical calculation, I have a modest boost, maybe 10%, 15% boost. But this boost is coming due to what? Is it coming due to delta 31? Is it coming due to delta Cp? Is it coming due to octant? I can't tell. So that is why there is a 3 degeneracy. Similarly, I see a small suppression, 10 or 15% suppression compared to my reference value, which means there is a boost due to one of the unknowns and suppression due to the other two unknowns. But which of the three possibilities is true? I can't tell. So that is why I have the other 3. So with precision measurement of theta 13, the original 8-fold degeneracy has split it into that. And the first data of NOVA, which came out in 2017, they had NOVA has seen a moderate increase compared to what is this so-called reference value I mentioned. And they had 3 solutions, which precisely is boost due to delta 31, boost due to delta Cp, suppression due to octant. That is one solution they had. Boost due to delta 31, suppression due to delta Cp, boost due to theta 23. That's the second solution they had. And the third solution they had was suppression due to delta 31, boost due to delta Cp, boost due to theta 23. So, pattern really looked beautiful in the sense. Exactly what we expect, and that's exactly what we. Now, given this 3-fold degeneracy, what can we do to break the 3-fold degeneracy? Well, here is where anti-neutrino data helps, but not completely. By the way, what's the time?
3:30.
Okay, I'll take another 10-12 minutes. Yeah, actually, let me go to explain it based on that formula alone. By the way, what I have written here is for neutrinos. Now, if I consider anti-neutrinos, we find that delta 31 greater than 0, then P mu bar to mu e bar is less than the reference, and whereas if it is less than 0, this is greater. So as far as the effect of the sign of delta 31 is concerned, neutrinos and anti-neutrinos have opposite effect. Similarly, delta Cp in lower half plane, P mu bar to mu e bar is less than P reference, whereas this in is greater. So in the case of in the case of delta Cp also, the effect on the anti-neutrino probabilities is ulta. But as far as octant, theta 23 greater than 45, P mu bar mu e bar is greater than P ref, and less than 45, P mu bar mu e bar is less than P ref. So as far as the octant is concerned, the dependence of neutrino probability and anti-neutrino probability on the discrete variable is the same, whereas as far as the delta 31 is concerned and delta Cp is concerned, the behavior is ulta. So if you have, so as I said, nova, first data of nova on nu mu to nu e gave me this threefold degeneracy. There is a modest increase relative to the reference. So the expectation, so if we take the anti-neutrino data, now the question is this increase coming due to this or this or this, or this, yeah, this or this or this. If the increase is coming due to this, then rather if these two are cancelling each other and that modest increase is due to this, the same feature should occur in antineutrinos also, because in antineutrinos this is ulta, so these two cancel in neutrinos, they will also cancel in antineutrinos, and the modest increase due to higher octant, which in the neutrinos we should see here also. But suppose this increases and this increases and this decreases. Wait a minute. I have to be a little careful here. Yeah, suppose this increases and this increases and this decreases. That also we can rule out. Sorry, I'm unnecessarily getting mixed up. Let me consider this solution first. This increases, this also increases, this decreases. If that is the solution, then anti-neutrino, increase here means decrease, increase here means decrease, decrease here means decrease. So in anti-neutrino, all the unknowns should decrease and the anti-neutrino probability should be very, very small. And NOAA has measured the anti-neutrino probability and they didn't find the anti-neutrino probability to be very, very small. So that this increase, this decrease, that solution is ruled out. But in the case of NOVA, it is very difficult to make a distinction between the other two solutions. So, yeah, let me explicitly write down. If solution for nu mu to nu e is increase due to sine of delta 3 1, increase due to delta Cp and decrease due to theta 2 3, then nu mu bar to nu e bar implies decrease here, decrease here, decrease here, and anti-neutrino data of NOVA rule it out. They don't find such strong suppression of it in their anti-neutrino data. So the two possibilities are increase due to sine of delta 3(1), decrease due to delta Cp, increase due to theta 2(3), or decrease due to sine of delta 3(1), increase due to delta Cp, and increase due to theta 2(3). This implies that modest increase in P mu bar to mu e bar also. In neutrino, the effect of delta 3(1) and delta Cp are cancelling out, leading to a modest increase coming due to theta 2(3). And same thing will happen in antineutrinos also, and that is actually what NOVA sees. So based on NOVA data, you cannot make a distinction between the two. But okay, we have T2K also, so combining NOVA and T2K, can we make a distinction? In principle, it should be possible, but the statistics in both experiments as of now are limited enough that we actually do not have an exact solution. And there is a possibility that data taken over the next 5 years in both experiments will resolve the problem. There is a possibility, but the following considerations are also being pursued very seriously. There is an experiment called DUNE, which is a future experiment. Yeah.
Just one question. You're looking at probabilities in matter as well as vacuum.
No. Vacuum probability is a derived quantity. It's a calculated quantity. It's not a measured quantity. Measured quantity but it is a matter because neutrinos are going through matter.
Okay. So both NOVA and T2K experiments, you're looking only at matter.
What they measure are matter modified oscillation probabilities.
Okay.
But
I think you wrote about vacuum.
No. I wrote vacuum. Okay, sorry, I have sun. What I'm saying in writing this vacuum, what I had in mind is I make one change at a time. Here I include the matter effect but keep delta Cp 0, theta to 345.
Okay.
Here I do not consider matter effect but consider non-zero delta Cp but keep theta to 345. And here again I don't put in matter effect, put delta Cp 0 but theta to 3 away from 45. I put one change at a time, but what the experiment measures, it definitely has matter effects included. But this is for considering one change at a time, and then how the changes combine to give me the final answer. That's all.
Also, here we are looking at only the deficit probability. Right?
No, I'm kind of looking at the oscillation probability, mu to nu e.
Sorry, yes. But you're not looking at the energy, but if you look at the...
If I look at the first, since θ13 is small, the number of events are somewhat small. So, but of course, people look at the energy dependence also. And if you have very good spectral information, yes, it is indeed possible. But in order to get answers based on spectral information, you really need enormous statistics. I mean, if you change these variables a little bit, spectra also change, but not so drastically that. So having spectral information helps, but the determining thing is the total number of events. People, when they do analysis, they do the analysis based on the spectral information. But if you sort of modify the spectra a little bit, 10-15% here and there, the answers will not change. So this DUNE has a longer base length, and of course if you have longer base length, you want L over E to be constant, so you need to have higher energy. Higher energy means matter effect is larger. So in DUNE, the change due to sine of delta 3,1 is roughly factor of 2 times change due to delta Cp. So in the case of nova, the change due to delta Cp and change due to matter effect, they are essentially of the same magnitude, and that's why this cancellation is occurring. But in DUNE, the experiment is designed so that the change in the magnitude, the change due to sine of delta 3,1 due to matter effects is twice the change due to delta Cp. So you know for a fact what is the correct solution. So that is how we hope to resolve the unknowns in 3-flavor neutrino oscillations. By the way, T2K has a slightly different strategy, but that will take a lot more time to discuss, so I'm not discussing that.